Hi there, my name is Jude Lykins, and for my digital final project, I attempted to create a rotating radar system that will measure the distance from the apparatus to an object or a wall and output that both orally and visually. Before I get into the nitty-gritty about how my project works, its central component was an Arduino microprocessor. So I figured I would start by going over what an Arduino is and its components. To begin, the Arduino is, as I said, a microprocessor or microcontroller board able to take in data, process it, and then output that data. It consists of a smaller microcontroller, input-output ports, analog to digital converters, and memory, both RAM, random access memory, and ROM, read-only memory. The smaller microcontroller is known as an AT Mega 328 microcontroller. It and by proxy the Arduino have a 5 voltage operating voltage and an input voltage from 7 to 15 volts, but ideally this should not exceed 12 volts so as not to overheat any of the components. The microcontroller has a 16 megahertz clock speed, meaning that every second there will be 16 million clock ticks. As for the I/O ports, the Arduino comes equipped with 14 digital input-output pins, 6 of which are enabled with pulse width modulation, which is used in this project. Additionally, there are 6 analog input pins, each of which connected to an analog to digital converter with a resolution of 5.9 millivolts, so up to 1023, so 10 bits. Each of these output pins have a recommended current output, the digital output pins. This is recommended to be 20 milliamps, but can go up to a maximum of 40 milliamps. And finally, as for memory, the Arduino comes with 32,000 bytes of flash memory or 32 kilobytes. Each of these components of the Arduino work in tandem, storing things in the memory, reading it from there, getting data from the input and reading it to the output, and using ADCs anytime an analog input is needed. The goal of my project was to build a radar-like system to measure the distance from an object and map that around the entire room. To do this, I hooked up a servo to a ultrasonic sensor so that the servo will spin the sensor around, getting a idea for how far everything in the room is from the sensor. I then wanted to output that distance both orally, so audially, and visually, so some type of screen. To do this, I used a buzzer that will change frequency, getting higher the closer something is to the sensor, and an OLED screen that will output both the maximum distance and a trace of the distance versus angle. Finally, I would like to control when the data is being read and when the servo is moving via a button so that it only activates once I push it down. This brings me to the first subsystem of this assembly, the ultrasonic sensor. As you can see in the diagram here, the ultrasonic sensor has 4 pins, a VCC, a ground, a trigger, and an echo. The VCC and ground are connected to power and ground respectively, as you might expect, and the trigger and echo pins are both hooked up to digital input pins. Specifically in my assembly, I connected the trigger to pin 13 and the echo to pin 12. The ultrasonic sensor works by sending out a chirp of very high frequency sound, and then waiting for the response of that sound, the echo, hence the echo pin. The difference in time between these 2 pulses can then be used to figure out the distance that an object is from the sensor because of the near constancy of the speed of sound. Next is the servo subsystem, which is what spins the ultrasonic sensor around to get a sweep of the entire room. It rotates slowly about the vertical axis and is limited to only 180 degrees, so we sadly can't get a view of the entire room. This servo uses pulse width modulation, so it has to be hooked up to a specific pin. In my assembly, along with this picture, it is pin 9. Based on the duty cycle set by the pulse width modulation, the servo will go to either 0 degrees or anywhere between 0 and 180 degrees. And we can control that via the Arduino. Next is the buzzer subsystem. This buzzer will play a tone proportional to the distance from the sensor. As you can see, one end is hooked up to ground and the other end is hooked up to a digital pin. In my assembly, this was pin 10. By modulating the frequency of the signal sent to this buzzer, you can increase or decrease the frequency that the buzzer then puts out. The next subsystem of this assembly is the most complicated one, the OLED subsystem. It took me a while to find good documentation on how to actually make this screen work, but once I found the correct files, it was actually not too bad and pretty straightforward of outputting the trace. My goals for this OLED was to output both the maximum distance, as you can see up at the top here, as well as a distance versus angle plot, where it will output a larger distance for farther things and a smaller distance for closer things. In this picture here particularly, this short section corresponds to my water bottle being placed close to the sensor, and hence there is a area of small amplitude for our graph. You can see here on the diagram that the OLED display has 4 pins, a ground VCC, which are connected to ground and power as before, as well as an SCL and SDA pins. I am not totally sure what these actually stand for, and in the diagram they go to analog 4 and analog 5, but the Arduino that I was using, the red board, has pins specifically for SCL and SDA, and so I hooked them up there instead, and it worked flawlessly. The final subsystem of this assembly is the button subsystem, which is simply connected on one end to ground and to the other end is tied high. This means that when the button is pushed, the circuit will be connected to ground and the voltage will drop. This voltage drop can then be measured by a digital pin and read into the Arduino, allowing it to know when to start rotating the servo and gathering data. Here is some of the, well, all of the code in the next 2 slides for the Arduino. Code is very boring to go through, so I will try my best to make this short. On the left here is just the initialization. We include 5 different libraries that are needed for the different components, set the screen height and the address for the OLED, create a servo object, and then create pin numbers specific for the button, trigger, echo, and buzzer. Next is the setup function, which is only run once at the very initialization of the function. It calls the serial begin, allowing us to read in data from the ultrasonic sensor, sets the pin mode to either input or output, depending on which pin it is, and then initializes the display as well. Then it puts the very beginning titles, particularly max distance and the distance versus angle in the top left of the display, and outputs it to the actual OLED. That brings us to the loop function, which is where the meat of the code is. It starts by initializing some more data and setting the previous max distance to the previous iteration's max distance, so long as that is not 0. It then checks if the button state is low. If the button is not pushed down, then it is still tied high as shown in the previous circuit diagrams, so this will not be true. However, once the button is pushed, ground is connected, so the button state goes to low as read above, and we will execute this chunk of code, which is when the system will actually start reading the data. It begins by writing the servo to 0, which causes the pulse width modulation to have a duty cycle of 0. That will set the servo to 0 degrees and allow us to start our measurement. First we do some more with the display, setting the max distance title, the distance versus angle plot, and then rotating our text to have the vertical distance label for our graph. Finally, it puts the current max distance next to the output, and then iterates our for loop. Now, this loop goes from 0 to 180 degrees, and after each iteration, it will set the servo to that position, send out the signal on the trigger pin, and wait for a response. When it does that, it'll measure the time between the initial pulse and when it receives the echo and store that as duration. Then we can divide duration by 2 because the sound pulse has to go to the wall and then back, and then divide that by the speed of sound, 12.91, to get the approximate distance to the object that our sound wave bounced off of. If this distance is greater than the current max distance, then we set our new max distance, update it, and update it on the display as well. Next, we generate a frequency based on this distance. You'll notice according to this function here that it is dependent on the previous max distance, such that if the distance were to exceed that previous max, then our frequency will actually be negative, causing the buzzer to emit a somewhat odd sound. This is expected not to happen, but is nonetheless a limitation of the system. The buzzer is then told to emit this frequency as a tone, and then the display draws a pixel at a height corresponding to this distance and an x coordinate, a width, if you will, corresponding to the angle that the servo is currently at. Finally, the data is outputted to the serial on the actual computer so that it can be read if desired. After the loop has finished, the buzzer pin is turned off and the servo is rotated back to 0. So, does this actually work? To prove that to you, I have a video here. Last time I filmed this, the sound did not work for this video, so I hope it does this time. Please enjoy.
Actually, you text me because I'll I might be working my ass off next week catching up.
I mean, whatever. I just think like good block.
No, I agree. I don't want to meet like a little bit at a time. I want to like get.
We found the good like it has a certain purpose and role. So if you like out and then you look at
I'm gonna like.
I said it to
try and block out of it.
35 miles an hour.
Now, you can see from this second plot that it has a significantly higher amplitude than the data retrieved from the very first run, which I believe you can see in the bottom left here. The reasoning for this is that the first run was the very first iteration of the button being pressed. So the maximum distance is equal to the hard-coded 300 centimeters that I put into the Arduino. This is an overestimate so as not to have any of that negative frequency sound. But as a consequence, it causes the graph to be somewhat vertically squished and not reach up to the very top of the screen. The second time iterating this loop, this problem was remedied because the previous max distance was stored and then set as a reference for the top of the blue section of the LED, as well as the minimum frequency of the buzzer. So, what are the limitations of this system? As mentioned before, the servo only goes 180 degrees. So if you actually wish to get a full map of the room, you would have to either take measurements, rotate the system, and then measure again, or find a 360-degree servo, which I have heard are more expensive. Secondarily, the ultrasonic sensor is not perfectly precise. If you are shining it at a faraway wall, it's going to somewhat average what it is seeing there. So it's not going to pick up on small handles on the cabinets or often even columns that are coming out as a protrusion from the wall. However, it gets the rough trend very well, as you can see from the previous video. And finally, an error in, well, not error, but limitation in my code is that the frequency of the buzzer and the maximum height of the OLED display are determined based on the previous maximum, which means that if our distance exceeds that previously set maximum, then the frequency dips down to a negative number, causing the buzzer to stop emitting a noise, and the trace will exceed the blue section of our OLED, placing dots in the text previously. I have not had a huge problem with this, but it is still a possibility. In conclusion, I had a great time working on this project and learning the vast possibilities of Arduino. It also taught me that ultrasonic sensors don't have a very high resolution, but the Arduinos have no trouble gathering that data, processing it, and then outputting the data how I see fit. I felt like this was a very good culmination of a lot of the things that I've learned. The coding of the Arduino felt very similar to C++, which I've taken in other classes. The whole system in general felt very similar to the CompSci 250 project from last year. So I felt like I had some amount of experience and was free to let my inner geek out, or however it was worded on the assignment. But I had a very good time with this. Another thing that I learned was that a finished product has been heavily debugged. On the very third day of working on the lab, I thought I would have to come in for maybe 15 minutes to quickly get some data, get a video of it working, and then leave. But the OLED had different plans, and I was spent the rest of the lab time debugging that portion. So good code is run well and run many times to ensure that there are no fringe cases. Finally, here are my references. As you may have noticed based on the code, a lot of it is not mine. And this is where I got the commands and the wireframe backbone of my code. Thank you very much for listening. I had a great time working on this project.